Filming a whiteboard is difficult. To get it where it's not casting a shadow on when I put my arm up is quite difficult. Yeah, so a torque converter takes the place of a clutch, like in a manual transmission. If you were to swap them around, if we go from a manual trans to an automatic, we get rid of the clutch that's actuated by a pedal and replace it with a torque converter. So what does the clutch do for a manual? It allows the engine to run
without running the
without driving the input shaft of the transmission. Okay. So with an automatic, we don't have the clutch pedal to release the engine from the transmission. So the torque converter takes the place of that. Start by explaining it like a fluid coupling. Commonly used in like heavy equipment. A fluid coupling and a torque converter are very, very similar. There's just one extra part if we have a torque converter. And in a fluid coupling, you have two components. So we have the engine. Let me get a darker pen here. So you have your engine, let's say. It's a really fancy engine.
That's a perfect looking engine.
And then we have our transmission. And let's put an output shaft in the engine. And we need an input shaft in the transmission. So output from the engine and input to the transmission. So the torque converter is going to go between the two, obviously. So part of our torque converter needs to be connected to the crankshaft of the engine, and part of the torque converter needs to be connected to the input shaft of the transmission. So the two parts that connect, the part of the torque converter that connects to the engine, we call the pump or impeller. I like to refer to it as the impeller because the pump gets confusing when we talk about an automatic transmission, because in the transmission itself we have a pump that pumps hydraulic fluid. So connects to the engine, and I'm just going to represent it like this, and it'll make sense why I'm kind of illustrating it like that in a second. But let's say that's our impeller. On our transmission side, connected to the input shaft of the transmission, we have a part called the turbine. And it can be illustrated pretty much the same way. So we're looking at the side view here.
Okay.
And we've got our engine crankshaft, it rotates. Within the torque converter, let's kind of draw a makeshift housing around the torque converter.
So the impeller would always be spinning.
Right, the impeller is always spinning because
it's coupled to the engine crankshaft.
Well,
flywheel.
Right, it's connected to the flywheel, but in an automatic transmission application, we call the flywheel a flex plate. So we have a flex plate that is bolted to the back of the crankshaft. Let's represent it with this green here. So there's our flex plate, and so our torque converter is bolted to that flex plate. So the whole torque converter, the whole housing of the torque converter rotates with the engine. Our impeller is part of the housing of the torque converter. So if our engine's running, the flex plate's turning, the housing of the torque converter is turning, the impeller is turning. Our turbine connects to the input shaft of the transmission, and ultimately is going to turn when all the conditions are met that need to be. I think I actually drew them rotating opposite directions. But the example I like to give here is two fans, like cooling fans that some weirdos sleep with at night, for the white noise or whatever.
Yeah.
Like your box fan. What happens if you put two fans facing each other, and then one of those two fans plug into the wall and turn it on? And let's say we turn it on low. and it's pointed towards the other fan. What's going to happen with the other
It
fan?
would turn the other fan.
It would
pull air
start to
through it.
rotate the other fan. Let's say on low, when the fan that's plugged into the wall is on low or at idle, the second fan isn't really turning. It might spin a little bit. But let's turn on our input fan or our impeller fan and let's crank it up to medium speed. Now we start to spin the output fan or the turbine fan more.
And that's where you said you would lose power through the torque converter all the time, right?
Right,
You're
because
never going to get
so
it to
now
spin at the same speed.
to take the example of two fans facing one another, and we have the input fan that's plugged into the wall, that's our impeller that's connected to the engine. So instead of plugging the fan into the wall, we're just going to connect the engine to it and run the engine. So now we're driving our input fan or the impeller. And with the example of the fans, we have ambient air being blown into the turbine or the output fan. In an automatic transmission torque converter, we have hydraulic fluid or ATF, automatic transmission fluid. And that fluid is inside the torque converter.
It's basically cycling it through the,
And you can think of the fluid just like the air that the fan's blowing.
yeah. It's,
So when the engine's turning at idle, it's pushing that hydraulic fluid towards the turbine.
okay.
But at idle, the fluid isn't transferring enough energy to the turbine to overcome the resistance of the wheels, the gear sets inside the transmission, the hydraulic pump that's in the transmission. There's too much drag on our turbine, on the input shaft of the transmission, for at idle the engine to move enough fluid with the impeller to drive the turbine. So as we give the engine throttle, we spin this faster, we put more torque out to the flex plate and to the torque converter. Now we're starting to drive more fluid harder, which means that fluid is hitting the turbine blades harder, and it's going to start spinning the input shaft. And ultimately, the more power output of the engine, the more it drives the transmission. With the parts we have now, let's get rid of our fluid. With the parts we have now, just an impeller and a turbine, we'd call that a fluid coupling, which commonly found in heavy equipment. There's only two parts. The impeller. I know that spelling. I'm not an English teacher, right?
Yeah, you're fine.
Impeller. And then we have the turbine. And it's just the two fans. The impeller fan is blowing fluid into the turbine fan, and it's driving the transmission. If we want to take our fluid coupling and make it a torque converter, we got one more piece we need to add. And that is another fan, essentially, but that fan does not turn. It's called the stator. And that stator is suspended between the turbine and the impeller, and it does not rotate. Stator. And ultimately, the job of the stator is it's suspended in the middle of the torque converter, and it's supported there and held there by a component called the stator support that actually is on the transmission side, but that's neither here nor there. We're not worried about that currently. But when the engine is outputting torque and driving the fluid in the torque converter, the stator helps redirect the fluid to change the angle that the fluid is flowing out of the impeller and hitting the turbine. And ultimately, the stator is redirecting the fluid flow at the optimum angle so that the turbine blades are getting hit at the correct angle with the fluid to collect as much torque and energy out of the fluid as possible. The only other detail, just in general, of a torque converter, it's just the three parts, but within the parts, the impeller and the turbine, they're just fans. The stator, it's a fan that's supported on a stationary shaft called the stator support. But in the hub of the stator there's a one-way clutch, meaning in one direction it doesn't rotate, but in the other direction it does. Because in certain states of operation, say on D-cell, when you let off the throttle and the engine is winding back down to idle, but our truck's going however fast, highway speed, whatever, the fluid flow through the torque converter, ultimately, we're soaking up a lot of energy from the drivetrain, and there's such a difference in speed between the engine and the transmission and driveline that this stator is able to rotate backwards. So it's going to lock in one direction to help redirect that fluid. But in certain scenarios where there's a difference in speed, difference in load versus engine output torque, the stator is able to spin backwards. Otherwise, it would just soak up a lot of energy and waste it through heat, because it would just be rapidly circulating that fluid. And, so we'll get into the one-way clutch in the hub of that stator when we get more detailed into this, but I kind of just want to give you bite-sized pieces.
Yeah.
So it's not too much to process. Instead of worrying about what the stator's doing and when it's locked and when it's unlocked and when it's freewheeling versus stationary.
I was saying, yeah, the stator seems like that's the complex
Yeah, and it's not even that complex.
part of it.
Can you think of any other like examples of things that you've used in your life, mechanical things that might have an example of a one-way clutch? Like as in it
I
locks.
immediately think of a ratchet.
A ratchet is a good example and that's a one-way clutch that we can change the direction of.
Mm-hmm.
In one direction it ratchets and doesn't connect the socket drive to the handle, and in the other direction it locks and connects the handle to the socket drive. My favorite example to use with a one-way clutch is your bicycle. You're pedaling,
Mm-hmm.
the one-way clutch is locked and it's locking the pedals and chain to the hub of the wheel and driving it. But when you stop pedaling, the one-way clutch in the back wheel hub allows the wheel to rotate with the hub sitting stationary. But as soon as you start to pedal again, you drive it and it locks, or the ratchet locks
Mm-hmm.
and drives the wheel again. So no different than what's in the stator. And it kind of, you can think of it as the same operation as bicycle. When you're pedaling, your one-way locks and drives the back wheel. But when you're going downhill and you don't want to pedal, the stator's able to freewheel spin backwards so that it's not soaking up wasting energy. Because we already lose quite a bit of energy through the torque converter, depending on what states it's in. There's always going to be slippage here. You're always going to lose something between the engine and transmission unless we add one more part. How could we, or how do we traditionally connect the engine and transmission rigidly together so that the RPM that the crankshaft of the engine is spinning is the same exact RPM that the input shaft of the transmission is spinning?
So you'd have to physically connect them.
Right, and how do we normally do that in other drive lines that we've talked about?
You'd use your clutch assembly. I mean.
Yeah, right. So, just like in the automatic transmission itself and how we actuate those clutches, we're going to add a clutch in here in the torque converter.
Okay.
That instead of actuated by a pedal and a pressure plate like a manual transmission clutch, we have a clutch in here that has a pressure plate that has an application piston that's a hydraulic. So ultimately, the transmission can feed hydraulic pressure to the clutch within the torque converter, and that's called the torque converter lockup clutch. So traditionally, it's changed in modern times, but traditionally in like old 4-speeds and stuff, it would only lock up the torque converter clutch when you're at steady speed, not much load, flat ground, driving, highway speed or whatever. Nowadays, the manufacturers are locking up the torque converter clutch in every gear. Why would you have any idea why they would change to just locking up the torque converter in top gear, 4th gear in a 4-speed? and why they went from that to trying to lock up the torque converter in second gear, third gear, fourth gear. We're up to 10-speed automatics now, you know, so, and they're locking up that torque converter clutch in every gear they can, even if it's only for a moment between shifts. What would be the driving reason behind why manufacturers would add the complexity to add control for the torque converter clutch lockup in every gear rather than just top gear? It's fuel economy.
Yeah, I was.
EPA regulation. The more the torque converter is slipping, the more you're wasting fuel energy because the engine's taking chemical energy in the fuel, converting it to mechanical energy, turning the crankshaft, and then we're putting that energy from the engine into the impeller and then driving the turbine, and we're losing all that energy there. So if we can lock up the torque converter clutch and lock the engine crankshaft to the transmission, that's less wasted fuel energy not going to the wheels. So ultimately fuel economy, tailpipe emissions. You hear me? Did they get that truck out?
Yeah, the truck's out.
Let me get you the paperwork so that you can, hey, my phone.
Yeah, I stopped recording about halfway through, but I got it all.